Okay, so last time we talked about ion beam induced separation. So now we talk about electron beam induced separation. So the idea is similar to the ion beam induced separation. So we have the electron beam. So we have the electron beam, and we have the gas injector. So we have the precursor gas that is injected, and this electron beam will decompose the precursor gas to form the volatile into the volatile and non-volatile component. So the volatile component is pumped away, and the non-volatile component become the deposit. So this is roughly the idea of the electron beam induced separation. Here are some examples of the E-beam electron beam induced separation. The first one is the world map. You can see this world map has very, very high resolution. So this scale bar is 50 nanometer. You see the edge is maybe just a few nanometer. But this one is a tape grew on the STM probe. Now this tape is grown by the electron beam induced separation. The last example is the metal deposit. This is the TEM image, metal deposit. So as you can see, there is no this material has lots of impurity, has 90% of carbon. This material may be a platinum, so it can be a PT or maybe tungsten, but it turned out to have lots of carbon. So in this image, so do you think the black color here, the dark area here, is this the metal or this is the carbon? Yeah. So the dark area should be the metal. The gray color here should be the carbon, because this is the transmission electron microscope. So when you have the metal, it blocks electrons. It's heavier, it will block electrons. That's why it appears darker. But this is opposite to the electron, opposite to the ICM. So for the ICM imaging, so when you have the metal, you get more signal, so you get brighter. So here's the comparison between the ion beam induced separation and electron beam induced separation. First, for the electron beam induced separation, there will be no sputtering or material removal. So this is the main advantage. The main advantage for the electron beam induced separation. But if we add some reactive gases, for instance, if we add this kind of gases, it can form a silicon. So it tetrafluoride. So when you add this kind of gases into the chamber, so electron beam can remove material because it will form the volatile product. So because we use electron beam, there will be no gallium impurity, but there is a lot more carbon impurity. So because there are too much carbon, so the conductivity is much worse. As you can see later on, it is 10 or maybe even 100 times worse than the ion beam induced separation. The separation speed for the ion beam induced separation is 10 times that of electron beam induced separation. So the reason I think is not hard to understand. So here you have the material here. So we have the electron beam come in. The electron beam will go very deep, but not much interaction on the surface. For the separation, we have the precursor gas molecule on the surface. So what happened on the surface is most important. For the electron beam, it goes very, very deep. But for the ion beam, like gallium ion beam, but we have the local interaction, so it's more efficient. It is more efficient to decompose the material to form the deposition. So for the high aspect ratio structures, ion beam induced separation is better than the electron beam induced separation for the high aspect ratio structures. So this one we have a slide actually later on. So look at this one. This is the high aspect ratio separation. You can see for the ion beam, so we have seen this structure. So this one has a 40 nanometer diameter, 45 micrometer height. This is extremely high aspect ratio. So this is possible for the casing of the ion beam, because when we have the ion beam like gallium ion, it will, the interaction will be very localized. But when you have the electron beam, come in. You see this one. This P means primary electron. So here, FSE, this is the forward scattered electron. So this is the secondary electron. But this secondary electron is caused by the forward scattered electron. This secondary electron is caused by the back scattered electron. This one is back scattered electron. So this is the secondary electron caused by the primary. Secondary electron caused by the primary electron. So when the electron come in, you can see it come in, go laterally. So when you come out here, there will be a separation here. There will be separation here. There will also be a separation here. Sorry. There also that be so that means so when you grow up, there will be lateral separation on those places. So then in the end, it's more difficult to have this kind of very, very tall structure. On the right side, so here we have the electron beam induced separation. This one is high aspect ratio, but compared to this one, it's far from, it's still not as good. So this one I use a very high energy, so 120 kilo electron volt. So this is only the height, maybe 100 micrometer, 100 nanometer. So we have this 120 kilo electron volt. Electron beam can get pretty deep with not too much lateral scattering. Then they get this high aspect ratio. But still, you can see it's not comparable to this deposition. But this is the high aspect ratio deposition. For the critical application, ion beam induced deposition is much more popular and more mature, because ion beam we can do the milling, remove the material, we can do milling, we can do the deposition. Deposition has higher purity and it is also faster. So electron beam induced deposition is good for the mask repair. So as we will see later on, when we use gallium ion beam to repair the mask, this gallium will implant into the mask, and this gallium will block the DUV light. But the electron beam will not have this problem. But for the critical research, so based on the paper I read more papers on electron beam induced deposition than papers on the ion beam induced deposition. That means it is popular for research. But because it has no gallium contamination and there is no damage by the ion bombardment, so the purity is not very good, but it can be acceptable if you use some other precursor gases. The precursor gas. This one not procurion, should be precursor gas with less carbon, with less hydrocarbon bond. So this hydrocarbon bond is the worst. This will give a lot of carbon in the deposit. So here is the mechanism. So we know that for the ion beam induced deposition, the mechanism is called collision catalytic, basically local heating by the ion bombardment. But for the electron beam induced deposition, so for example, we want to deposit germanium using this German gas. We use German gas to deposit germanium. So first, we need to decompose. But here we don't call it, we call it dissociation. It become germanium H3 plus H. Then this hydrogen, hydrogen will also become later on. In the end, you get the germanium deposition. So this reaction happens after the ionization of the precursor. So the total process is called dissociative ionization. Now this process can be calculated, can be simulated by it's called encounter model. So for the encounter model, it is like a collision. So you have two objects to collide. We have the collision, the cross section will be important. So larger the cross section, the higher the probability of the collision. So you can consider the cross section as the probability of this chemical reaction. As you can see, the peak is here. This is the peak. It's about 50 to 100 electron volt. 50 to 100 electron volt. Now this one is the schematic. So you have this curve is similar to this one. Again, the peak here is 10 to this one is 10 to 30 electron volt. This one is the measured and estimated dissociation cross section. This one is the log scale. So this is the linear scale. So this is the linear scale. This is also linear scale, but here is the log scale and log scale. If we do the linear scale, it will look something like this. So it will be something similar to this. So the conclusion is very clear that the cross section peak at 50 to 100 electron volt. So this is the energy for the secondary electrons. This is energy for the secondary electrons. As a result, the secondary electrons is the most important for the deposition. But at the beam center, so I draw it here. So electron beam come in. So this center part, we have too many. So even this energy is too high, not the primary electrons, they are not efficient. But because the number, we have too many of them, then there will be the deposition induced by these primary electrons. For the nearby, those areas here, the nearby the nearby area is done by secondary electrons. But for the beam center, the primary electron is also important because the number of the primary electrons is so high at the beam center. So here is the deposition material composition. So as we know, there is a lot of contamination, lot of carbon. Why we have lots of carbon? For the normal chemical vapor deposition process, for the regular CVD process, this is a pure thermal process. So we have the WCO6, for example, plus heat, 200 degree, give you, the CO will be gone. So for this one, WCO. So we have this bond. So this bond will be cut. So leave behind tungsten. You get very pure deposition. For the case of electron beam, so you have the same thing, WCO. So electron beam is very energetic. So it can easily cut this bond. If this chemical bond is cut, then this carbon will stay with the tungsten, so become the impurity into the tungsten. So because for the electron beam, so we know the energy for the electron beam is order of 10 of electron volt. For the temperature here, 200 degree. How much energy for 200 degree? So we know that for the room temperature it is 25 milli electron volt. It's only 25 milli electron volt. So 200 degree maybe 50 milli electron volt. With that 200 degrees, you see the thermal energy 50 milli electron volts is so much smaller than this electron energy. As a result, the electron energy is very powerful. It can cut any chemical bond. But for the thermal energy, it can only cut this bond, this weak bond. So for the case of the ion beam, ion beam is in between a 200 degree and this electron beam. It is a heating effect. It is a local heating effect, but it is also more powerful, more energetic than this thermal effect. As a result, you still get some carbon in the tungsten by ion beam, but not as much as the electron beam. So this is the graph. At the bottom is the electron energy loss spectrum. So it's called EOS. Electron energy loss. So this is called electron energy loss spectrum. So this one is done inside a TM. So what do you do? So you have the sample here. This is your sample. The electron come in and the electron come out. So here energy is E. Here energy become E prime. So the energy loss equal to E prime minus E. So this one is the electron energy loss spectrum. So this is the energy loss. So where is this energy loss? So this energy is lost to kick out a inner shell electron. You have the inner shell electron. So when this electron here, if this electron here kick out a inner shell electron, then it will lose energy. So the energy needed to kick out inner shell electron is the for example EK or maybe EL over the shell, over the K. This is for the K shell. This for the L shell. L shell over the material. For this case, you can see for the case of carbon, the EK for the case of carbon, the K shell energy you need 285 electron volt. You need a 285 electron volt. You lose 285 electron volt to kick out this K shell electron. So we have seen previously that another particle can also do the same thing. So what is that? So we can also use X-ray. We can also use X-ray to kick out a inner shell electron. The difference is that for the case of electron, it lost part of energy. This energy here is 200 keV, for instance. This can be 200 keV. Come here, it will be 200,000 minus 285. So it only lost part of energy. But for the case of X-ray, so the entire X-ray photon is absorbed. Because we cannot absorb half of the X-ray photon, so the entire X-ray photon is absorbed. So now let's look at that back. X-ray absorption of X-ray by the carbon. So we have seen this before, so now I will show you again so you know what it is about. Yeah, so it is here. Okay, you can see This is the carbon, this is the carbon. The energy here is also 285, so 285 electron volt. So it's the same. So again, 285 electron volt. So here is the deposit. So we know we have lots of impurity. So the resistivity is pretty high. For example, for this case, for tungsten. So we have a tungsten here. Tungsten using WCO6. So the resistivity is 0.01 ohm centimeter. So this is for the pure tungsten. The resistivity should be better than 10 micro ohm centimeter. But this one is 0.01 ohm centimeter. For the case of ion beam induced separation, we have seen this before. You can see this is also the same gas, so we get about 200. This one is about 200 micro ohm centimeter. So this one 200, and this one it is 0.01. This is much higher than the ion beam induced separation. So when there are no carbon, using WF6, no carbon, it is better, but still it's not very good. It's still higher than the ion beam induced separation. For the gold, 0.01 is very bad because those methyl group, FAC, TF, those are all organic group. When there are no, this one has no no hydrocarbon bond, no organic group, no hydrocarbon bond, chlorine, phosphine, F3, then you get purer. So this is about 10 times of the pure gold. And similar for other metals. So basically, for the electron beam induced separation, if you just want conducting, it's okay. It is conductive. If you just want conduction layer, it is conductive, but it's not very good conduction. So now let's look at a proximity effect. As we have seen this one, so when electron comes in, it will go around. So the nearby area, this area here and this area here, there will also be deposition. So this is called a proximity effect. Because when you deposit this pillar, you get the nearby area. There is also a little bit, not too much, a little bit deposition. So we have seen this slide before. So those are the popular precursor gases for the deposition of different materials. The most popular one is the platinum. This is the most popular for the metal for the focused ion beam. So it is used for the capping layer, protective cap layer, a circuit added a mask repair, a TM sample lift out. Tungsten is also popular. I think what we have here is tungsten. But this one is not as popular as platinum, but it is okay. And then we have the carbon. So carbon is also conducting. Conductivity is not as good as tungsten and the platinum, but it is conducting layer, and it has the lower contrast for the substrate, lower contrast to the substrate. Then we have the insulator layer. This one is called the TOS, tetraicyl oxosilicate, TOS. This is used to deposit silicon dioxide. But this is the insulating layer. When you do the circuit edit or do something, you want to protect the circuit in the end, to protect it with the insulating layer. This is for that purpose. The gold, I have never seen it because this precursor gas is very expensive. Some labs have it, but normally the shared facility does not have gold. This one is used to help the etching of the silicon or silicon nitride or silicon oxide. This is for the etching purpose. There are also other gases, other gases for different materials. So now let's look at the application of focused ion beam. The most obvious application is that we can use the ion beam to do machining, to do the nano or macro machining process. For example, this kind of complicated structure can be produced by the ion beam machining. So you start with the 20 micrometer tungsten wire, then you use ion beam to cut it, then you weld it. Then you cut it, then you weld. You have here, you can see this part here. Then it can be welded. After it is welded, it's taken out. So how to do the welding process? How to weld? You have one part, another part. Here you have like this needle here and this metal piece. So how to weld the two parts? This can be done by the deposition here. if we deposit some, for example, if we deposit some platinum material in this area, then this part and this part will be welded. So after it is welded, you can take it out and you put it down here. Then you can weld this part onto this hole there. Then you can cut. Then you can cut off. You cut off here. So you cut off from here. You can use iron beam to cut it off. Then you leave behind on the top. Then you can move around. You do the milling. You mill away the central part. Then you can you can mill another part like this. Then you can attach this one onto it. After it is attached, you do the welding again. Then you do the final machining and polishing. Then in the end, you get something like this. This is another few examples. This is called a detonator linear actuator. So you have the circular like a coil. This is like a bullet. When the bullet comes out, it is rotating at high speed to maintain the direction. So this is a surgical tool. You use iron beam to cut something like this. So those are the machining. This one is the iron beam induced deposition. So how to deposit some material, some shape like this? This one is this is also iron beam induced deposition. So the key is the diamonds like carbon. You can see you can also deposit some structure like this. So how to make those complicated 3D structures using iron beam or electron beam induced deposition? Yeah, you will remember the process is here. So what do? So you have the substrate. You have the iron beam come here. So you move laterally, and you do the complicated movement. Then in the end, you get a complicated 3D structures. So here's another example of the application of focused iron beam. So if you want to know what is inside in this can, you do the iron beam cutting. You can cut a hole like this. Then you can do the imaging. You can do the iron beam imaging or electron beam imaging to see what is inside. Those are the images. On the top, there is the paint. But actually, as you know, for the electron beam or iron beam signal, there will be no color. You got signal strong, but no color. Those color here, and those color here is fake color. So now we look at this part. So here it is bright. So here it is dark. So while here is dark, here is bright. So this is because of the channeling effect. So we have the channeling effect. You have less signal of the secondary electrons, so it become darker. We have seen this before. So if you want, this is a very popular application of iron beam. So you want to know what is inside of the circuit. For example, two companies, AMD and Intel. So if AMD wants to know what is inside the chip made by Intel, so he can buy a CPU. They use the iron beam to cut something like this. Then it will know, CPU Intel have this kind of circular design. Then they can copy. At the same time, Intel can buy the AMD chip and to look what is inside and to see whether AMD has copied the circular design of the Intel. But this is called to look inside. There is a term for it. To look inside, it's called reverse engineering. It's called reverse engineering. So you get something, you want to see what is inside. This is very useful. For example, if you suspect somebody steals your patent, then you can do this kind of reverse engineering to check it out. So we can also image the biomedical biomaterial. This one is the a cell. This is the stomata guard cells of the coriander leaf. So how to do this kind of cross section? So it has to be done at liquid nitrogen very low temperature. At the liquid nitrogen temperature, everything is solid, it's frozen. You can use iron beam to cut it. Then you can do the iron beam imaging or electron beam imaging. The next one is the human fibroblast nucleus. Here, see particles here. This particle here. So those particles is the cobalt particle. So in our human body, we have a lot of cobalt particles. Again, this is done at a low temperature. And from here we see the cobalt maybe is the nutrition that we need. So now let's look at TM sample preparation. Now this one is the most important application for the focused ion beam. So how to prepare the TM sample? It used to be very, very hard work to prepare the TM sample. It's very tedious work. So this is the old way to prepare the TM sample. So you have the sample here. First, you cut it. Then you do the mechanical polishing. Then you do the dimple grinding. You grind it to something shaped like this. Then you use argon milling to thin down. So in the end, this area here may be 50 nanometer. This process may take 1 day, take a very, very long time. It is not precise. For example, if you want to look at this spot, maybe in the end you look at this spot. So you cannot, it's not very precise to decide which part to look at in the end. But if you do the TM sample preparation using focused ion beam, then you get more precise. But what do you do? First, you look at the sample. This is the sample. First, you decide where is the interest part you want to see. So you want to see this part. Then you make a mark. You cut away. You use ion beam to cut away this side, and also cut away this side. You cut away this side, cut away this side. Then you leave behind a thin slice. So the slice here is about 1 micrometer thick. You should cut from here. You cut from the edge to the center. This is again you cut from edge to the center. So this way, in the end, what you see the cross section will be something like this. You have here you cut. This is the slice here. You cut. So you see, if you do the cross section along this line, you will see something like this. So when you have this slope is because of the ridge operation. So wheel mill, even you get ridge operation, you have this slope here, you have another slope here, and this is the slice you want. So afterwards, you have something called end effector. It's called end effector. This is a metal piece. So you put this end effector into the near the ion beam. Then you use the ion beam to cut. You use ion beam to cut a shape like this. Then you try to clip this shape onto this slice. How to do this? This is very complicated. So what you do? You know that. So here is the sample here. Here you have the ion beam here. So here you have the electron beam. So this is the dual beam. You have the ICM, scanning electron microscope, scanning ion microscope. So this gallium ion, this ion microscope can tell you the in plane of the sample. You do the alignment. In plane, in plane of the sample. So the ICM can tell you what the height. This image is the ICM image. This image is the electron image you see from the side. So when you lower it, you use this ICM to see that you lower slowly. For this active plane on the sample surface, you use the ion beam. So we have two kinds of images that you can locate. You can click onto the sample. And then you cut away here, you cut away here, then you take it out. So you take it out. So afterwards, it can be thinned down. This is still too thick. Here is like a 1 micrometer. 1 micrometer is too thick. Then you can rotate, move around, you thin down. You thin down to about 100 nanometer. This is then below 100 nanometer. It is good enough for the transmission of the electrons. Finally, you can flip it over. You get this one. The diameter for this one, diameter for this one is 3 millimeter. This will fit into the TM. This is the way University of Western Ontario do it. I got all those pictures from the University of Western Ontario website. But that one nowadays is no longer popular. So you can see again, so this is the cross section. If you look at this cross section, it will be something like this. Like this is the cross section. You can see this is the taller, lower, and then lower and taller. So the cross section is like that. A better way than this method is to use the welding. You can use the welding process. you have this you have this manipulator, you call the micro manipulator. You put it very close, then you deposit a layer of the platinum. You have the platinum deposition here, then it is welded. But once it is welded, you cut off around, you take it out. So nowadays FIB mainly use this method rather than this clip method. Another possible is to use the nano gripper. Actually, I have never seen this one in the TM. This is it is doable, but it's not so easy. It's complicated. So what do? You have something like this. You have one slice here. But this part is the gripper part. This is the arm. So the arm, you do some laser, you shine some laser beam. When you have the laser beam, it will be heated up. When it heated up, there is the thermal expansion. Then this part, they will become closer, and then you clip it out. Thank you.